start looking at the applications of exponential functions. So we've been doing what I would call the boring stuff for the last few days, where we've learned how to work with logarithms, how to work with exponents, how to do the math behind what we're going to learn how to do. But there is application behind exponential. Y'all with me? There is application behind exponential functions. Notes. Okay, there is application behind exponential functions. And so they come in two different places, and they're both very important. And probably will hit a lot of you in your major choice, one way or the other. There are two places their exponential functions are very commonly used, or one with money, so it hits all of you somewhere because you're all going to take out a loan or something, so that's an important one. And the second one is in biology and bacteria growth, population growth, and things like that. So those are the two places where exponential functions connect to real life. And so we're going to start looking at those examples or those applications today, and we'll spend a couple days on those. So a colony of bacteria grows according to this function, and that is a 0.045t for those of you farther in the back, where n is measured in grams and t is measured in days. And it asks you to graph this function in your calculator and find an appropriate viewing window. So get your calculators out if you haven't yet. I hope you already have. If you aren't doing bell ringers, you need to start. Okay, so I've put the function in my y equals. I haven't done anything else yet. It says use an appropriate viewing window. Well, we know a little bit about graphing exponential functions. You would agree with that, right? 100 is what? If I were graphing this by hand for some reason, what does the 100 do to it? When you put a 100 in front of an exponential function. This will be on your next test. It is the y-intercept. It's the vertical stretch, right? It stretches it up 100. So if you are completely lost on that, you need to go back over that first test graphing stuff. It will show up again on chapter 5b test. So the 100 is the vertical stretch. So would you agree that this exponential function is going to be bigger than 100? It is exponential growth because the exponent's not negative. No reflections over the x or y axis. So we're growing and we're starting at 100. Does everyone agree with that? So in my window, I'm going to leave my x max at 10 for now. We'll see what I want to do with that later. But my y max, would everyone agree it needs to be much bigger than 100? So I'm going to go with 500. We'll see how that does. From 0 to 10, 500 was plenty big. Does everyone agree with that? It's growing, but not too terribly fast because the number beside the t was 0.045, which kept it kind of slower growth. And we'll look at what that does to it today. But do I see what I feel like I need to see? So, if it says this on your homework, make sure you show me a quick sketch. Doesn't have to be a great sketch, but just something that lets me know that you... If I wanted to by hand sketch, I'd put a grid on there and get a better sketch. But I just want an estimate. I think you already answered part B, but let's try again. Determine the initial amount of bacteria, or the amount of bacteria at time 0. 100, how do you know? Look at your table. You can put 0 in your table. Bailey said, hey, that vertical stretch made my y-intercept 100. You've got a couple of ways you could see that, but there are 100 bacteria at the beginning. What is the population after 5 days? How could you find that? Table, and what would you plug into your table? Good. Put 5 into your table and I get 125.232. Now, I do want you to go ahead and show me that you found the decimal. If you want to make a conclusion that, hey, it's about 125 bacteria cells, then you could, but go ahead and show me that you used your calculator. Any questions about that problem? So this is a lot of what your homework's going to look like tonight, is working with exponential functions. Okay. Exponential growth and decay in the context of bacteria growth or population growth is what I call the PERT formula. Now your textbook uses the A equals A subscript 0 e to the kt, but that formula on the left is the exact same thing, and it's easy for students to remember. It's the PERT formula. P-E raised to the RT. How many of you have seen that before? Somewhere? Awesome. Where? Just out of curiosity. Miss Lowe. What about you two back there? Who'd you have, Caitlin? Miss Lowe, so same place. Not in regular algebra 2. Didn't see PERT in regular algebra 2. What about in science class? Anyone seen it in science class? Nowhere in science class? Well. Do what? A is the final amount, P is the initial amount, R is the growth or decay rate given as a decimal. Really quick, let's talk about that. A lot of students get confused about that and they'll ask, do I need to put this as a decimal or a percent? Really, that's a bad question because what is a percent always? Anyone know? It's always a decimal because what's the word percent mean? Does anyone know? Per 100, right? Percent per 100. So 90% means 90 out of 100, which is 0.9. So anytime you see a percent mathematically, that always means a decimal. So it's never 90. It's always 0.9. If you ever see that, anytime you're going to use it, always change it. Did y'all know that? No? Yes, no, maybe. T is the time, and most of the time it's in years, but it could be in another unit. So if it's money, it's always in years, but we'll talk about that later. Every now and again, a textbook will use the PERT formula for money. It's not very realistic. The PERT formula is used for bacteria and continuously compounded growth. But sometimes textbooks will do it anyway. Are we supposed to do number 3? Okay. Does everyone have this written down? The formula? You do not have to write both down. They are the exact same thing. Just know if you see this, it's the same formula. The A subscript 0 is the amount at time 0. But I think it's a little bit more complicated notation. So, but both work great. So, a colony of bacteria grows according... Oh, is that the same thing as about... Yes.
Lily rushing?
I do. She is taking a quiz. Do you need her right now?
She can come whenever she's done.
Okay. You're welcome. I guess you heard that, Lily. Okay. Same function as the bell ringer, but we are asking some different questions. A colony of bacteria grows according to the same function that was on the bell ringer, where N is measured in grams and T is measured in days. What is the growth rate? Well, we just learned that the growth rate is the R, right? So what's the R here? 0.045, or if I wanted to represent that as a percent, what would that be as a percent? 4.5%. Both of those are correct answers. 0.045 or 4.5% is the growth rate. How long will it take the population to reach 140 grams? How could I find that? What am I trying to solve? $140 is the final population, right? So 140 equals 100 e to the 0.045 t. So I'm solving for t. Because how long? So I want to know the time it takes to reach 140. Do I have options on how to solve this? Yes. Sure. In your table? No, it won't let you type y's in your table. Only x's. Man, it would be nice if it did let us type y's in. Good question. We have a couple of options on how to solve this. Agreed? We could do it how? Intersection in the calculator, or we could do it by hand. I'm going to show you both. They both work great. By hand, I'm going to start there, and then I'll go intersection. Do I care how you solve it? No, you do it however you want. So 140 divided by 100, why would I do that first? Why would I divide by 100 first? What type of equation is this? Exponential, right? So I need to get the exponential equal to a number. And then I rewrite using a logarithm. Or take the natural log of both sides. Natural log of 140 over 100 equals 0.045t. I would write this down even if you prefer the calculator option. Why is it good to have a backup plan? In case you don't have a calculator, you probably will. What's another reason? Do it faster. How many of you get stuck on your window sometimes? Can't get your window to set. Yeah, so if you can't get your window to set, this is really the reason. If you can't get your window to set, do it by hand. If you can get your window to set, do it in the calculator. It doesn't matter to me, but sometimes we struggle with that window stuff. So this is a way to do it if your window fails you. Get t by itself, so divide by the 0.045, so I get natural log of 140 over 100 divided by 0.045. Second option, and I'll go ahead and type that in, so show you how to type that in. Natural log is the ln button, 140 over 100, divide by 0.045. 7.477 is what you get by hand. And then the other option, because we like to have two options, in your calculator, I'm going to put 140 in Y2 and look for that intersection. I do happen to see it on the window I've already chosen, but if you hadn't chosen a good window, you may have to do some rearranging. Second trace 5, enter 3 times, and I get 7.477. You should get the same thing either one of those ways. So. Again, when I do things by hand, I'm not trying to replace the calculator. I'm trying to give us a backup plan for when the calculator doesn't help. Okay, any questions about that? Last question is, what is the doubling time for the population? Well, what do you think that means? When does the population equal 200? That is a very common question that math textbooks will ask. is how long does it take it to double, or what is the doubling time? I'm going to work it both by hand and in the calculator. Divide by 100. I have a question. What if they hadn't given me the 100 and I didn't know how much I started with? Would this number still be 2 when I divided? Oops. I rewrote. Or took natural log of both sides, however you want to think about that. So I get 0.045t. Divide by 0.045. So I have natural log of 2 divided by 0.045. In your textbook, and it's not something I make you memorize because I feel like you can do it in the calculator or by hand, and I like to minimize how much you have to memorize. Because your brain only has so much space in it, right? But there is a formula in your textbook that it's called the doubling time formula. And it's natural log of 2 divided by the rate. Do you see why it would be natural log of 2 divided by the rate? Tripling time would be natural log of 3 divided by the rate. Makes sense, right? You don't have to memorize that because you can use your calculator to solve, but just know it's there. I'm going to put 200 in Y2. You will notice that this intersection does not fall in the window I have chosen. Do you agree with that? So what do I need to do? Good. Which part needs to change to 20? The X max needs to change to 20. Everyone agree with that? Am I going too fast? Y'all are pretty quiet this morning. Is it just Monday? Just Monday. Okay. Wait, are we doing okay though? And then second, trace 5, push enter 3 times. I get 15.4. That's the same thing you would get if you did natural log of 2 divided by 0.045, I hope. 15.403. I think our time was in years. Days. So it takes 15.403 days for our population to double. The other question was 7.477 days. Any questions about that? Good. All right, let's look at this one. Radioactive decay. So this is another common example for exponential growth and decay, except this one is decay. That function, I can make it bigger for you. No, I can't. Everyone write this down while I'm reading it if you can't read that. A of t equals A, little subscript 0, e to the negative 0.087t. Negative 0.087t. What do you immediately notice with that negative up there? What's going to happen to an exponential function when you put a negative up there? It's going to reflect over the y-axis, which means instead of going up, it's going to go down, so it's going to decay. So iodine-131 is a radioactive material that decays according to that function, where A sub 0 is the initial amount present, and A is the amount present in T days. Assume a scientist has a sample of 400 grams of iodine. I'll give you a minute to write, and then we'll work the problem. Part A is, what is the decay rate? that's an easy answer, isn't it? Anytime it asks for the rate in an exponential function, I just pick out the r in the PERT formula. So it's negative 0.087 or negative 8.7%. Both of those would be acceptable answers. Does everyone agree that those two things say the exact same thing? If we know what the word percent means, they say the exact same thing. How much iodine 131 is left after 10 days? Well, before I can answer that, I really need to write this function completely, don't I? What is this function missing that I could fill in? The initial amount. And what is the initial amount? 400 grams. So they made us fill something in. Could they have left the formula completely off and just given us the rate and the initial amount? So you can see if eventually they probably will do that and just give us the rate and the initial amount, and then we'll have to fill in the rest. But so how much iodine 131 is left after 10 days? What am I going to do? Say that again. Table and put 10 in for t. Okay. First I need to go to my y equals and change my function, because I still have the last one in. So I need to change my function to 400 e, pull this up for you, to the negative 0.087x. I'm going to go ahead and delete the 200 out. Okay, now before I graph this or anything, let's talk about what it should look like. What's the 400 again? It's the initial amount, so it's still going to be the y-intercept, right? Except this time after 400 I'm decaying. So this is an exponential function going down. You know they have a horizontal asymptote at y equals 0, so 0 to 400 would be perfectly good for my y values on a window. Now for this question, I don't even have to answer that, but it's always good to think about what does this graph look like, make sure I haven't done anything wrong. So my window, my y's, 0 to 400 would be plenty. If you wanted to go 0 to 500, you could, but 0 to 400 will be plenty. Because the highest it's going to be 400, because from there on it decays. And time doesn't go negative, so for real world application purposes, my x's can start at 0. For this question, I'm just going to go to my table and type in 10. Because I want to know the amount of bacteria left after 10 days. And so I get 167.581. Bacteria, or iodine 131 grams. Any questions about that one? When will 100 grams be left? How am I going to do that? When will how do I find when 100 grams will be left? Plug that in for A of t. So I want to do 100 equals 400 e to the negative 0.087 t. Again, I'm going to work it by hand, and in the calculator I'm going to show you both. At first, how many of you wanted to do them all in the calculator at first? Are they getting pretty quick by hand? Do they feel like they're kind of all the same thing? You heard Jacob say it's faster by hand. Well, he's had this class before, or one very similar. So he's going, I've done this enough times. These are really fast by hand, right? Now, at first, they may not seem fast by hand, but once you do a few of them, they get really fast by hand. You have options, though. Take the natural log of both sides, or you could use the rewrite, whichever one you prefer. Those of you who had Miss Lowe, Jacob had me, but those of you who had Miss Lowe, do y'all feel the same way about this by hand? Pretty quick by hand, or you kind of like the calculator better? It doesn't matter. You can use either one. Divide by the negative 0.087. Or, your other option is go to y equals and put 100 in y2. You will notice that in the window I have up, I do see an intersection. If not, you could adjust the window accordingly. But I do see one. So I can go to second trace 5, push enter 3 times, and I get 15.934. Just a mental note. I know I'm sitting over here and I'm doing that because I'm using a calculator. I still can see you look down at your cell phones. So just make sure those stay put up. And that is in days. How do I know it's in days? It said T was in days up there somewhere. So after that many days, there will be 100 grams of the sample left. Okay, any questions so far? Now they did tell us the 400, but I want to show you something because this is something that you will be asked often. I'm going to pretend they did not tell us the 400. I'm going to pretend I don't know that. Just pretending purposes. What is a half-life? Anyone from science know? It is the time it takes for half of the substance to be left in a radioactive decay problem. It is. So if I started with 400 grams, then half would be 200. So on this particular problem, I could do that, but I'm going to pretend I don't know. The cool thing is, I don't know if it's cool, but good enough. If you were solving this by hand, wouldn't your first step be to divide by a sub 0, whatever that number is? If it's 400, you divide by 400. If it's 800, you divide by 800. If this is truly half of that, wouldn't you always just get a half equals e to the negative 0.087t? So I want you to know that sometimes they won't tell you the initial amount, and they'll still ask you the half-life. And you can still find it. If you know the decay rate, you can find the half-life whether you know the initial amount or not. Carbon-14 has a half-life. It's a specific half-life, and it's the same. That's how they carbon date things. Y'all know what I mean by that? They can carbon date by looking at how much carbon's left, because they know the decay rate, they know how much is left, so they can go back to see when that substance started to decay. There are some variables they have to take into account that get a little tricky, like was it sitting in water or not? That stuff makes carbon dating a little more fishy. But other than that, that's how they use half-lives to determine how old something is, how old an artifact is. Take the natural log of both sides. Divide by negative 0.087. Remember how I said there was a formula for doubling time? There's also a formula for half-lives. It's always natural log of a half divided by the rate. Again, I'm not going to make you memorize that formula, but it's good to know. The other way to do that would be to go to your calculator, go to y equals, and type, what would I type in for y2 to find a half-life if my initial sample was 400? 200. If they don't give you an initial sample, make one up and then put 200. Right, put 400 and 200, 150 or 10 and 5. You can do however you want, but put something with a half in there. Graph it. And find the intersection. And I get 7.967 years. I mean, not years, days. This problem was in days. Okay, any questions about that one? How are we doing so far? Good. I'm going to go ahead and give you your homework. I have one more problem to do. I think we'll have plenty of time, but just in case. 45 through 55 odd. What does that mean? Those are in the back of the book. Now, every time I assign odds, there is the temptation to just go write all the answers down. Will I ever know? Probably not until the test, and then it will glaringly be obvious, because you will fail. So don't do that. That would be stupid. Practice for the test. Go through and try it, and then check your answers. If you miss one, go back and try it again. See if you can get to the answer, but make sure that you can get there on your own. Gage, are you up? Stay with me. So the odds, you can check them. So there are essentially two that you could possibly miss. Every other one, you should get the right answers on those. You should try them until you get the right answers. If you can't make it work, come ask me. But you know the right answers on all but two of those problems. These probably have parts to them, so be aware of that. Not all of them, but... Okay, let's look at this last one. At the end of a sales campaign, the daily sales of your product fell, and it gives you S of T. Is a model of the sales in thousands of dollars. I'm reading a word problem. I'm going to underline that. Why is that important to me? I need to know it's in thousands. If I get an answer of 100, it's actually 100,000. So I need to be aware of that. Where were the sales at the end of the ad campaign? Notice it says after the end of this sales campaign. Right, so this is the model after the end of the sales campaign. So would you agree the first time after the end of the sales campaign would be at time 0? So what were the sales at the end of the ad campaign? Oh, you could. What am I going to put in the calculator? Chris, stay up. Gage, you awake back there? Good. Put 0 in for T. What am I going to get when I put 0 in for T? 400. How do you know I'm going to get 400? Have y'all noticed that when you put 0 in for T, you always get this number here? Why do you get that number there? What's anything to the 0 power?
What's that number?
This little one, it is negative 0.07 T. anything to the 0 power is 1, and 1 times 400 is 400. So anytime you put in 0 up there, you're going to get that number in front because anything to the 0 power is 1. Why 400,000 and not 400? It's in thousands of dollars. When did your sales fall under 150,000? How am I going to do that? I'm going to set this equal to 150. Why just 150? I heard someone say it. It's in thousands, so how can I solve that? I can do it by hand, or I can do it in the calculator. Which way do you want to see? Working it out. Are y'all okay with me only working it out one way? The calculator. I've done 3 today, the calculator, so you've kind of gotten a feel for that too. I have no preference on which way you work these. Just make sure that one of the 2 options you're being successful at. It wouldn't be a bad idea to be successful at both options because then you have a backup plan. Natural log of 150 over 400 equals negative 0.070. Remember, to undo an exponential, you use a logarithm. To undo a logarithm, you rewrite as an exponential. And why do I keep using natural log on these problems? Because it's base E. If it were some other base, I'd use some other logarithm. All of the problems today have been base E because they've been that exponential growth, continuously compounded interest problems. Type that in the calculator. We get, say that again. Awesome. And today's, how do we feel about today's stuff? Okay, so today we again focused on solving real-world problems that involve one formula, and that was the exponential growth and decay formula. We will look at other formulas tomorrow. I don't. You can go back.